So we have these three identities, the sum and difference formulas. Sine and cosine. Sine of alpha plus beta is sine, cosine, cosine, sine. Call that the sum identity of the sine function. And with this one, by replacing beta by minus beta, after all, this is supposed to hold for all angles alpha and beta. And we remember this, instead of saying sine alpha cosine beta plus cosine alpha sine beta, we usually just say sine cosine plus cosine sine. That's easy to remember. What do we get out of this? Alpha plus minus beta is also sine of alpha minus beta. So we say if this holds for beta, it holds for minus beta. Beta is arbitrary. And then we have cosine of minus beta. I'll write that in here. Plus cosine alpha sine minus beta, right? So we get that instead. But now cosine of minus beta, cosine's an even function, right? So if cosine's even, I can just take the minus away. Call it cosine beta. Sine of an angle is odd. Sine is odd, so the minus comes out. I can put it over here. Now what I've done by putting beta equals minus beta in here and using the even and odd properties of cosine and sine, I've got a difference identity for sine. Remember the sine and cosine identities, the sine identities plus and minus. Also, cosine of the sum of angles, have this formula, cosine, cosine minus sine, sine. Putting the angles in the same order, alpha, beta, alpha, beta. And unfortunately, with cosine, with sine, we had plus with plus and minus with minus, but cosine, we have plus with minus. And then if we put beta replaced by minus beta, this holds for arbitrary angle beta, we get the difference identity, right? The left side becomes cosine alpha plus negative beta, is cosine alpha minus beta. And I've got cosine alpha, cosine minus beta, minus sine alpha, sine of minus beta. We have a difference identity, right? But now cosine of minus beta, cosine's even, so I can take the minus away, right? That's just cosine beta. Sine of minus beta, sine is odd, so the minus comes out, makes this plus. There is the difference identity. Replace beta by minus beta and use the even and odd properties. And I've got this difference formula for cosine. So if I call those 1, 2, 3, and 4, then these can be used to get similar results for tangent. Put a short proof here of this one. I left out the hardest proof, which is this first one. We can get a sum and difference formula for tangent. Suppose I take tangent of alpha plus beta. How can I evaluate that? Get a sum and difference formula for tangent. Well, tangent of any angle, alpha plus beta, is the sine of that angle divided by the cosine, right? So this is sine divided by cosine of the same angle. Well, I have some formulas for these, right? Sine is sine cosine plus cosine sine. And the cosine of the sum is cosine, cosine minus sine, sine. And we have that. So there is a sum identity for tangent, but really we'd like to write it all in terms of tangent. How can I switch that over to make it tangent? Right. What you can do, and I need to move the camera over, don't I? So I'll divide top and bottom by the same thing. Let's rewrite this sine alpha, cosine beta. I'm sorry, we won't do too many proofs today, but cosine alpha, sine beta. Top over the same bottom as I have cosine, cosine minus sine, sine. And so this is the same thing, but now I'm going to divide the numerator and the denominator by cosine times cosine. Cosine alpha, cosine beta. All the way across, right? It'll be the same quotient because I divided numerator and denominator by the same thing. They cancel. Now look, these cosine betas cancel. These cancel all of them. You can think of this as just one. Here I've got tangent alpha. Here I've got tangent beta. These cancel. This becomes tangent beta. This becomes tangent alpha. And what I find out is that I have tangent plus tangent, 1 minus tangent times tangent. There is a sum identity for tangent. We can call this equation 5 tangent of alpha plus beta is tangent plus tangent over 1 minus tangent tangent. This is the one I have the most trouble remembering. Equation 5. And finally, if you replace beta by minus beta in that one and use the tangent is odd, so you can pull the minus out. This one becomes tangent, place beta by minus beta, you got tangent alpha minus beta equals tangent alpha plus tangent minus beta over 1 minus tangent alpha, tangent of minus beta. There it is. And pull the minus out, minus the tangent of minus theta is minus tangent of theta, so you pull the minus out and put it here. Pull the minus out and put it here, make this a plus. There's the sixth one. We have 6 sum and difference identities, 2 for sine, 2 for cosine, and 2 for tangent. And then these we looking at before for sine and cosine anyway. These allow evaluation exactly by hand of any trig function of a multiple of 15 degrees. So we've got some new angles in addition to special angles, which are multiples of 30 and 45. Any multiple of 15 degrees now, like 75 degrees or 105 degrees, I can now do exactly by hand. 15 degrees is pi over 12 radians. So we multiple pi over 12 radians. We only did sine, cosine, and tangent. Can you imagine what we do for the other three? is use the reciprocals. If we want cotangent alpha plus beta, we take 1 over the tangent of alpha plus beta. But the trick here to doing these is it's just a one-step method, is by writing whatever angle we want that's a multiple of 15 degrees as a sum or difference of special angles. That's it. Rewrite the thing as a sum or difference of special angles and use the sum or difference formula, and you can evaluate any trig function. And for, let's put in parentheses, for cotangent, secant, and cosecant, use reciprocals of 1 through 6. Okay. So here's, I don't reiterate too much what we were looking at before, but suppose I want sine of 5 pi over 12. How can I evaluate that exactly? Do I know I can evaluate that exactly? How do I know? Yeah, it's 5 times pi over 12. It's a multiple pi over 12, an integer multiple, I'm saying. Integer being 0 plus or minus 1 plus or minus 2. All the numbers with nothing after the decimal point are integers. Integer multiple pi over 12, so I can do it by hand. And a lot of calculators will do this too. So if you bought an expensive calculator, you can check your answer on there. What I do is I rewrite this as sine. Well, I could put 4 pi over 12 and pi over 12, right? That won't help me. Why not? Pi over 12 is a special angle, right? Special angles are multiples of pi over 6 and pi over 4. That won't work. Well, let's try something else. 3 pi over 12 and 2 pi over 12. That makes 5 pi over 12. Those special angles? Sure. So you just rewrite it, right? 3 and 2 is 5 pi over 12. And let's see, this is 3 pi over 12 is pi over 4. That's a special angle. 2 pi over 12 is pi over 6. Sure enough, a multiple pi over 4 and a multiple pi over 6. I've written as a sum of special angles. So that's the trick. Now you apply equation 1. Say the sine of alpha plus beta, sine cosine plus cosine sine. Remember, with the sine, plus goes with plus and minus goes with minus. Put the angles in the same order. Pi over 4, pi over 6, pi over 4, pi over 6. And this is exactly equal to the sine of 5 pi over 12, but these are special angles. I can do them all. Make sure that camera is all the way on. Pushing the edge of the board here. So now we got the edge of the board. All right, now when I choose these angles to be nice and small like that as acute angles, I can just use triangles. So I'll say, here's the 45, 45, 90 triangle. We'll call it pi over 4 since I'm using radians. The sides are root 2 over 2, root 2 over 2, and 1, and the one I memorized. You can scale it up by any number, of course. So sine is opposite over hypotenuse is square root 2 over 2. Cosine is also adjacent over hypotenuse, square root 2 over 2. Now for the pi over 6 angles, I need the other triangle. There's pi over 6 in the corner. This is 1/2 square root 3 over 2 and 1. Having memorized that triangle, I notice that, let's see, the cosine is adjacent over hypotenuse, adjacent to this angle over this square root 3 over 2. Opposite to the angle over the hypotenuse for sine is 1/2. Square root 2, square root 3. Remember the product of the square roots is the square root of the product is square root 6 all over 4. And this one is square root 2 over 4. Since they have a common denominator, I can add the numerators over that common denominator. This is exactly square root 6 plus square root 2 all over 4. So there was the sine of 5 pi over 12. So that's the first thing you do with these now. Too much of this. But now we can do tangent. We got tangent up there. Cosine. Suppose I wanted to calculate the tangent of minus (955 degrees). How about that? 965, I'm sorry. It's 865. Yeah, there we go. Okay. 885 degrees. When you get these large angles, there's a couple things you can do to make your day a lot easier. The first one is, can I do that exactly? How do I know I can do that exactly? Yeah, it's a multiple of 15. How do I know that? A couple of ways I can tell. One is to try and plot this. This is 720, which is 2 rotations, plus 165 degrees, right? Except minus. Let's put this. So I'm going to do this. I'm going to first pull out the minus and call this minus the tangent of plus 885 degrees because it's odd. You don't have to do this, but these odd properties sometimes make it a little easier. I won't have to deal with so many minuses in here now. Minus, 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 minus. It's just one sitting out front. Now, 885 degrees, let's put it, is 2 whole rotations plus 165. And then 165, if I think about it, is here 15 degrees short of 180. And whenever one of these angles comes a multiple of 15 from an axis, it will be a multiple of 15, right? All the axes are 90 degrees apart, so they're all multiples of 15, all the quadrantal angles, the ones that go down the axes. And so if I'm 15 degrees from an axis like that, it's automatically a multiple of 15. Well, I know this one can be done exactly because it's 15 degrees from a whole thing. Moreover, I don't have to look at 885 degrees and write it as a sum of angles that have 885. All coterminal angles have the same trig function. So I'll just rewrite 165 degrees, taking out 2 whole rotations. So that's what you can do for the big angles. Take out all the whole rotations to make it easier. Take out minuses. If it's an even function, you get rid of it. If it's an odd, you can take it outside like that. And now I've got an easier problem, minus the tangent of 165 degrees. There's my tangent formula, 5. If I just write this as a sum of special angles. I know that I can, because right is 15 degrees from an axis. Suppose I write it as 150 plus 15. Will that help me? No, because 15 isn't a special angle, right? I want a multiple of 30 or 45. I can, however, write it as 35 degrees plus 30 degrees, right? Multiple of 45, multiple of 30, those are special angles. Now, I'll use equation 5 here for the sum of the tangent of the sum of two angles, calling this alpha and this beta, and say tangent of alpha plus beta is tangent plus tangent over 1 minus tangent tangent. Okay, now for the 30-degree angles, I can use the special triangle, 1/2 √3/2 and 1. But for the non-acute angles, I'll go to the unit circle. Measure on 135 degrees. Say that it leaves an angle of 45 degrees to add up to 180. They're supplementary. Drop the perpendicular and figure out the coordinates of the point. Well, the cosine and sine are evidently minus √2/2 and plus √2/2 because I'm going to left and up. Tangent is y/x is -1, right? Tangent 135 is the quotient y/x. Now, I've got -1 plus tangent of 30. Is opposite over adjacent, 1/2 over √3/2. The 2's are both denominators, they cancel. So I'll get 1 over √3. -1 plus 1 over √3. 1 minus -1 times 1 over that one. Then the object is to simplify this and set the algebra on these. Sometimes the hardest part. Let's carry that minus in. I can take minus the whole numerator and call that 1 minus 1 over √3 over the denominator 1 plus 1 over √3, right? So I'll leave the denominator the same, 1 plus 1 over √3, and take minus the numerator, and that'll be this. Now I've got compound quotients. There's multiple things I can do here. I would like to get rid of those compound quotients, so I'll multiply top and bottom by √3. And get √3 minus 1 over √3 plus 1. And it's still not simplified. Why is that not simplified? All right, I've got a radical in the denominator, so I want to rationalize this. This would be about 2 points off still. I told you the algebra is sometimes the hardest part on here. How do I rationalize this expression? I can multiply top and bottom by the conjugate of this by using conjugate of denominator. I want to get the radical out of the denominator. So when you see an a plus b square root c, the conjugate of it is a minus b square root c. The conjugate of a minus b square root c is a plus b square root c. So they're conjugates of each other. Since I see 1 plus square root 3 here, I'm going to multiply it by 1 minus square root 3. And in order that I don't change the quotient, I'll multiply the top by the same. So multiply top and bottom by the conjugate of the denominator gets the radical out of the denominator, right? Now, multiply these out by FOIL. Square root 3 and minus square root 3 is minus 3. And I've got plus square root 3 outside, minus square root 3 on the inside. Plus 1 times plus 1 is plus. And the radicals always cancel if you multiply by the conjugate. On the top, these aren't conjugates, I'll have to multiply out. This time this is minus 3. This time this is plus square root 3, and this time this is plus square root 3, so it's plus 2 square root 3. And this time this is minus 1. There we go. So evidently I got minus 3 minus 1 is minus 4 plus 2 square root 3. And at the bottom I have minus 3 plus 1 is minus 2, and I'm still not finished, right? What do I need to do now? Maybe I cancel these 2's, huh? Can I do that? Can't do that, right? I have to cancel factors. 2 has to multiply the whole top and the whole bottom. Be a factor. So, right, factors are things that are multiplied together. What I'll do is I'll factor 2 out of the top. In fact, I'll factor out minus 2. I'll call this minus 2 times 2 minus square root 3, right? So that this times this is minus 4. This times this is 2 square root 3. And then minus 2 on the bottom, think of it as times 1. I can cancel minus 2 multiplying the whole top with minus 2 multiplying the whole bottom. Factors cancel, right? Factor the top, factor the bottom. Now I've just got 2 minus square root 3. So all that reduces down to this. There is the exact tangent of minus 885 degrees. Right? Well, once you're able to do those kinds of problems. But it'll be very good when you come out of here doing algebra. When I took trigonometry, I got better at algebra. When I took calculus, I got better at trigonometry. So you didn't have to use it all the time. It'll be the way it works. This will make you good at your algebra. How about this one? Because I wanted to evaluate the secant minus 7 pi over 12. How about that? What's a good thing to do first on that? Yeah, get rid of the negative. Secant is even, so it just goes away. I can just as well write that as secant of plus 7 pi over 12. That's easy, right? So because secant of minus theta is secant of theta, the even property. Secant and cosine are even. All the others are odd, right? Cosine, I like to think cosine is reciprocal to even functions. All the rest are odd. So this one, the minus nicely goes away. Now what's the secret to evaluating a multiple of pi over 12? I just write it as the sum of special angles, right? So I'll write this as 3 pi over 12 plus 4 pi over 12, right? And observe the 3 pi over 12 is pi over 4, a special angle. 4 pi over 12 is pi over 3, a special angle. Now to evaluate secant, I write it as 1 over cosine. And apply the cosine identity. Cosine alpha plus beta, my equation 3 is cosine cosine minus sine sine. Well, you put them in the same order, pi over 4, pi over 6, pi over 4, pi over 6. There's the exact expression for it. I can use the special triangles. We've already seen these. Pi over 3, I'm sorry, not pi over 6. We haven't done pi over 3 today. That's this angle here. 30, 60, 90 triangle. So its cosine is 1/2. And its sine, this opposite over adjacent, is square root 3 over 2. We recall the sine and cosine of pi over 4 is square root 2 over 2. Problem. And since they're over a common denominator, this is square root 2 over 4. This is minus square root 6 over 4. What I've got is square root 2 minus square root 6 all over 4. Except this is supposed to be 1 over all this stuff. Right, this was the denominator, so it's 1 over all that. And what I've got now is 1 over square root 2 minus square root 6 all over 4. By common denominator, I add the numerators over the common denominator. Now 1 over this is the reciprocal, so I've got 4 over square root 2 minus square root 6. And how do I reduce that? That one. This is like the conjugates, right? If I see square root minus square root or square root plus square root, I multiply by the same with a plus in here. So I'll multiply top and bottom by square root 2 plus square root 6. Multiply top and bottom by the same thing. It won't change the quotient, but now these will get rid of the square roots, right? Square root 2 is 2. Plus square root 12 minus square root 12 cancels. I can just take this one times this one and get minus 6. Right? Everything else cancels. Up on top, I've got 4 square root 2 plus 4 square root. Well, let's just leave it alone. Let's call it 4 times square root 2 plus square root 6. Well, let's see. That's 4 times square root 2 plus square root 6 all over minus 4. We can cancel the 4s and leave a minus, and what we've got is minus square root 2 minus square root 6. That's simpler. Now we can finish. We got, look at that. We didn't want to leave that here. What a mess. We had compound quotients and we had, now we got no quotient at all. All right, feel comfortable with all of those? Then there's some problems to simplify some expressions and do some identities. We're going to be able to do some problems like this. Good. We'll go with the cosine of the arc cosine square root 2 over 2 plus arc sine square root 2 over 2. How about that? What can I do with that? No. I'll just call this alpha and beta. Oh, it's cosine alpha plus beta. If I can do that, this by equation 3 for a cosine of the sum of two angles is cosine of the arc cosine of square root 2 over 2 right? Cosine of the sum is let's put it in slowly here. Cosine of the sum is cosine minus sine, right? Or I put in alpha, beta. This is just a complicated alpha and beta. So arc cosine square root 2 over 2, arc sine square root 2 over 2, arc cosine square root 2 over 2, arc sine square root 2 over 2. Alpha, beta. And now I can do it because cosine of the arc cosine of square root 2 over 2 is what? Cosine always does on arc cosine whenever it's defined, right? Cosine of arc cosine of an angle always gives the angle of the number, either gives the number back or is undefined. Well, we can do square root 2 over 2 because it's between plus and minus 1. This is just square root 2 over 2. They undo each other, right? How about this one? How can I do this one? It's trig of inverse trig, right? You can evaluate this directly in your calculator, but trig of inverse trig function we can always do. We make the triangle with this theta equals the inverse trig function I see, which equivalently is sine theta equals square root 2 over 2. Which means I can make this side square root 2 over 2 and this 1. Step 1, Pythagorean theorem. Guess the last side, I already recognize this triangle. If I use the Pythagorean theorem applied to this triangle, it will give me square root 2 over 2. And then step 3 is to evaluate the cosine of the arc sine. That's just the cosine of theta because I made the triangle that way, but cosine is adjacent over hypotenuse, right? Adjacent over hypotenuse is square root 2 over 2. So this one doesn't normally happen. The cosine undoes the arc sine, but in this case it does. It gives back square root 2 over 2. And minus, how about the sine of the cosine? You can use 3 steps again. And it's actually the same triangle, right? This triangle, this angle is also the arc cosine of square root 2 over 2. And then you find this side. Sine, again, will give square root 2 over 2 like this. So it's the same triangle. Setting up so cosine theta is square root 2 over 2. Now gives the sine of the arc cosine is square root 2 over 2. And then sine of the arc sine undo each other and you get square root 2 over 2 here. Evidently, this one comes out to be 0. This minus the same. There's a few identities to verify down here. Well, that additional thing you can do with these new identities is verify new identities, meaning make some new, derive some new identities, make some proofs. Remember those 3 rules of thumb I gave before for proving identities? It's been a while. But you apply your algebra techniques, getting rid of common factors and putting things over a common denominator, those kind of things. And then you apply trig identities and you replace everything with sine and cosine. You can verify a lot of identities. We can now do the same thing with one more rule, add to our old rules. Rule 0, which is get one angle. Two, one, then you apply algebra by eliminating compound quotients. Cancel common factors. Put over a common denominator. Those three things you use a lot. Then you apply a trig identity. Simplify. And then three, finally, you can write in terms of sine and cosine only. And for an equation, you work both ends to the middle. But these were the three simplification rules I had before. So I'm going to add this one rule here. We can use these sum and difference rules to get one angle in each trig function. Still on here. Make sure. Yeah. Okay, so I'll add this one up at the front, and now we can prove some. This is abbreviation for functions. We can try and establish some new identities that have sums and difference of angles in them. Here's one here. A. Well, I wanted to verify that tangent of x plus pi over 4 is equal to tangent x plus 1 over 1 minus tangent x. Nobody memorizes this identity, but you can figure it out from the identities we had. And on some of these, you kind of use that duck rule. If it looks like something you've seen before, you try and use that. But if I take my extended identities and start by first getting one angle, well, this is the tangent of the sum of two angles. I'll start off by using equation 5 here and rewrite this in terms of single angles, right? If I think of this as alpha plus beta, I can write it as tangent plus tangent over 1 minus tangent tangent. All right, where I put in x and pi over 4, x and pi over 4 in order. Maybe I've memorized by now the tangent of pi over 4, 45 degrees. Right? It's this side over this side, opposite over adjacent. Oh, this over this is 1, so this is 1. This is tangent x plus 1 over 1 minus tangent x times 1. Oh, there it is. Huh. So if this looks kind of like your tangent of some formulas, that gives you a hint. But whenever you see a tangent of a sum, what you now do is you use these identities to rewrite it. And now we can prove some new identities, such as this one, right? Sometimes you want to simplify this to that or something like that. You'll just call that the only example on that. So try those on the homework. It's just the idea is when you want to prove an identity and you have a trig function of a sum, you just immediately write the sum or different the sum identity. If you have a trig identity function of a difference, you immediately write the difference identity. Then you apply your old rules before, trying to drive the two ends to the middle. But each step of the way, we're going to get some new identities that we can use. That one look okay, hopefully. All right, now this is where you really want to keep up on the homework. So try all these homework problems out of section is that? Let's see. 7.2. Let's do one more, because there's one that we haven't done something like. I don't want to be too short on examples here. Let's do one last example here. If sine of A is 2/3, my cosine of B minus 1/4, with A and B, the interval of angles pi over 2 to pi. The square bracket means include pi over 2. The round bracket means don't include pi. Find what is the sine of alpha plus sine of A plus B. Whenever you see a sine or cosine of sum, just immediately write the formula. Say by formula 1, sine of the sum is sine cosine plus cosine sine, right? Putting alpha and beta again. Go. And I know the sine of A is 2/3. Cosine of B minus 1/4, but what am I going to do about these other two? How about that? It's the cosine of A, it wasn't given. Here's what you can do. If you know the sine of A and the quadrant, you can find all 6 trig functions, right? Remember that? If you're given a trig function and a quadrant, so I'll say cosine of A is, by the Pythagorean identity solved for cosine, is plus or minus square root 1 minus sine squared. Okay, right? And I know what sine is a plus or minus. Yeah, it's in quadrant 2, 90 degrees to 180 degrees. In that quadrant, cosine is negative, so I'll put negative here. So it's going to be minus the square root of 1 minus sine was 2/3 squared. Right? But I can calculate cosine from sine if I know the quadrant. This is minus the square root of 1 minus 4/9, right? Squaring 2 and squaring 3. This is minus the square root of 9/9 minus 4/9. Putting them over a common denominator makes 5/9. Square root of the quotient is the quotient of the square roots of positive numbers. If I have minus square root 5/3, if I simplify that. Similarly, I need to find sine B, but I'm not given it to it. I can do the same thing by the Pythagorean identity solved for sine. Sine is minus the square root 1 minus cosine squared. Right? And I know cosine is minus 1/4. So this is minus the square root 1 minus 1/4 squared. Well, it's minus the square root of 1 minus 1/16. Minus 4 squared is plus 1/16. But 16/16 minus 1/16, putting over a common denominator, is 15/16. 16 is a square, so I can rewrite this as square root of the top. Square root of 15 over square root of 16 on the bottom is 4. So that's that one. This will be cosine A minus square root of 5/3. Sine B minus square root of 15/4. There it is. So I can calculate this one as, let's see, this is minus 2/12 plus, because these minuses cancel, square root 5 and square root 15 is square root 75, the product, right? 12. And then square root 75 simplifies, right? This is square root 3 times 25. 5 square root 3, right? Square root of 25 is 5. Square root of 3. All right, so this will be minus 2 over 12 plus 5 square root 3 over 12 makes 5 square root 3 minus 2. Kind of a tricky problem, yeah.
So if
Did I mess it up? Oh, golly. That's in quadrant 2. Yeah, setting to be positive. Why did I put minus on there? Yeah, it's quadrant 2. I should have put that. Thank you so much. That's plus, plus, plus. Should I do this wrong? Plus 15/4. Yeah. So this should have been plus here. That makes all this minus. It's minus 5 square root of 3 minus 2 all over 12. Well, thank you. All right. Now these things are going to start to build. We're going to use these sum and difference identities to derive some more identities that are very useful, called double angle identities. We were just showing that we could derive some new formulas using these identities we came up with. These are some of the most important ones, so important that you want to memorize these. You want to memorize 1 through 6. Those are all useful. And by the way, there's a shorter way of putting those, I think we said, not today. Sine of alpha plus or minus beta. Sine, cosine, plus or minus cosine, sine. Plus with plus or minus with minus gives the first two identities. This is 1 and 2 together. Cosine alpha plus beta, plus or minus beta. Well, cosine alpha plus beta was cosine, cosine minus sine, sine. All right. That was equation 3. And if we had minus, we had plus. So here's 3 and 4 together all in one. So there's really only 3 identities memorized. Switch plus to minus and minus to plus to get the other 3. Tangent alpha plus beta, equation 5, was tangent plus tangent over 1 minus tangent tangent. And equation 6, you just changed all the pluses to minuses, the minuses to plus. So we'll put minus over plus here, meaning use all the top ones, plus, plus, minus, or all the bottoms, minus, minus, plus. And now you've got these all compactly written. They're not so bad to memorize. So you want to memorize all those. Moreover, we can use those to prove some more that are used quite frequently in mathematics called double angle identities. And so this will be an illustration of some of the proofs that also derive some more identities you want to memorize. And the first one, I bet you can see these proofs immediately, is this. So let's be equation 7. The sine of a double angle, twice an angle. 2 sine theta, cosine theta. You want to memorize that one. You see how to prove that one, though? How to prove that one using these. This goes all the way to the end. Because why? In this one, in equation one, the sum angle, the first of these with plus, you put beta equal alpha, right? You get sine alpha plus alpha. Let's do it this way. Alpha equals beta equals theta. So put both these equal to theta, and then you get sine theta plus theta equals sine theta cosine theta plus cosine theta sine theta, right? So in the sum formula, you put alpha and beta both equal to theta. Now the left side is 2 theta, sine of 2 theta. Now this is sine, cosine, and cosine, sine. You can multiply in either order, so it's 2 of these, twice sine, cosine. There it is, right? There's no more than that. You put alpha equals beta equals theta in the sine equation, you get that double angle formula, sine of a double angle. Furthermore, we can take cosine of a double angle by a quick derivation. See how nicely these easy identities come out of the ones we already memorized? Cosine of a double angle. Suppose I use the second one. Put alpha equals beta equals theta on the second one. Now I've got cosine theta plus theta equals cosine, cosine minus sine, sine with everything theta. Cosine, cosine minus sine, sine. Alpha and beta both equal to theta. Well, this is cosine squared, right? And this is sine squared. So remember, cosine squared plus sine squared is 1. Moreover, cosine squared minus sine squared is cosine of double angle, right? So cosine 2 theta, right, the left side is cosine 2 theta, is this, right? So there it is. The double angle formula for cosine is that cosine 2 theta is cosine squared theta minus sine squared theta. And finally, you have this one, tangent of 2 theta is 2 tangent theta over 1 minus tangent squared theta, but you can see where that one comes from. Just put alpha equals beta equals theta in the last one. And you get tangent theta plus theta equals tangent theta plus tangent theta over 1 minus tangent theta tangent theta. Well, the right side, I have 2 tangent theta on the top. On the bottom, tangent times tangent is tangent squared. And tangent of theta plus theta is tangent 2 theta. So there's the proof there. Putting theta, alpha equals beta equals theta in the sum of angles formula for tangent gives you this. Simplify the left, simplify the right, there it is. All right, so you want to know all of these things. Let's put a star by all of them. These you have to memorize, but the idea is these proofs are very important because once you've seen the proof, you have a tendency to auto remember this. Just imagine this one with alpha and beta equal, right? And that's all you have to do to memorize these. So these come a lot easier. So there's 9 formulas, but it's sort of 3 formulas and a little bit of memorization how to figure them out. Now, this is a classic problem with these. We'll make this note. We now know if we have value for sine theta, cosine theta, quadrant, we learned before we can find all 6 trig functions, right? We can now, in addition to that, find trig functions of double angles also. So of double angles as well, double angle 2 theta, as well as theta. So there's the example. Suppose I wanted to find, suppose sine x is 1/8, not coming from a special angle. I don't know what angle has that. Has theta x in quadrant 1. Find what is the sine of 2x? About that. Sine is 1/8. What's the sine of x is 1/8. What's the sine of 2x? Well, whenever you see a sine of a double angle, think of using the double angle formula. I want to put out a common mistake. I've seen a lot of students do this at this point. Sine of 2x is 2 sine x. What's wrong with that? It's not an identity. You can't do it. This notation is just brevity for meaning the sine function of 2x. You can't just pull the 2 out. It's like taking square root 2x and just pulling the 2 out, right? It's not true. You can't pull it out. There's implied parentheses here. It's the sine function of 2x. So you can't just pull the 2 out. What can you do? Equation 7, sine of 2x is 2 sine x cosine x. That's what it is by equation 7. So don't make this mistake of pulling 2's out of here. Use the identities, right? They don't come out. You have to use the identity. Don't pull 2 out of the square root. You don't pull it out of the sine function either. All right, now sine x is an 1/8. Got that, but what's cosine x? What do I find cosine x? Remember before we said if you knew one trig function in a quadrant, you knew all 6 of them, right? How do we do that? We had, for instance, the Pythagorean identity. If we know sine, we know the cosine. By the Pythagorean identity solved for sine, for cosine is plus or minus square root 1 minus sine squared, right? Sine squared plus cosine squared equals 1 means that cosine is, right? You solve that and you get this equation for cosine. Maybe I should remind you, huh? Sine squared plus cosine squared equals 1. That was our identity we memorized. If you subtract sine squared, and now you square root both sides, you get this. So this is the Pythagorean identity solved for cosine. And now here's where the quadrant comes in. In quadrant 1, all 6 trig functions are positive, so we scratch out the minus. Sine we were given is 1/8, so it's a square root 1 minus an 8 squared. Square root 1 minus a 64th, right? And you do like in the other problem, you write 1 is 64 over 64. Because to subtract, you need a common denominator, right? 64 minus 1, the difference of the numerators over the common denominator, makes this square root 63 over 8 square root of 64. Well, the top reduces too. Do you see how the top reduces? (63) is 9 times 7. 9 square root of 9 is 3, so we should really write this as 3 square root of 7. Square root of 64 is 8. So there we go. the cosine of x is 3 square root 7 over 8. So the sine of the double angle is 2 times an eighth times 3 square root 7 over 8. We said before that if you know one trig angle in a quadrant, you know all 6 trig functions in a quadrant. One trig function in a quadrant, you know all 6 trig functions. Now, not only that, you know that all 6 double angles, trig functions of all the double angles. So let's see, this is 2 times 3 times square root 7. If I think of this as 2 over 1, it's top times top times top over bottom times bottom times bottom. 1 times 8 times 8. Well, part of this cancels. The 2 cancels part of the 64, and you write this 3 square root 7 over 32. There's that one. How about? And moreover, we can get all the others. For instance, suppose I want the secant of 2x. What is the secant of 2x? Well, I don't have a double angle formula for secant, right? Just like the sum and difference formulas, I'm only going to do it for sine, cosine, and tangent. Those are the 3 in your calculator, so then they're the ones you need most. And moreover, you can do the other 3 as reciprocal. So I'll just write it as 1 over cosine 2x, and you apply the double angle identity for cosine. Cosine 2x by equation 8 is cosine squared x minus sine squared x. And now I can find the secant of a double angle. So you can see now you can get all 6 trig functions this way. Now we just found that cosine was actually 3 square root 7 over 2. Sine was given as 1/8. Oh, I'm sorry, 3 square root 7 over 8. And so I've got that expression, cosine squared minus sine squared. One over, let's see, 9 times 7 is 63 64ths minus 1/64. Whole thing is 1 over 62 64ths, or 64 over 62, or 32 over 31, looks like. Huh? There we go. There's the secant of 2x. Let's get too far ahead. Let's do this one. I don't want to jump too far ahead trying to do too much today. Let me just try one more here. So for example, suppose I say that tangent x minus 8 find tangent 2x. This one's a little easier. With now let's just do that. Well, all I gotta do is apply equation 9 now, right? If I know a trig function of one angle, of a single angle. In a quadrant, I know all 6 trig functions, right? But I don't have a quadrant. What am I gonna do without a quadrant? Well, it turns out on this one, I don't need the quadrant. I just use 9 directly, and I'll say tangent of 2x is 2 tangent x over 1 minus tangent squared x. These can be a lot to memorize, right? 1 through 9. But again, 9, just think of what is the sum formula is tangent plus tangent over 1 minus tangent tangent. If you can remember the first 3 with plus or minus switch, then just think, what if alpha and beta were both equal to theta? I'd have tangent plus tangent, I have 2 tangent over 1 minus tangent times tangent, tangent squared. So the proof C is immensely helpful in memorizing this. So if I know this sum and difference formula, I can figure this one out every time I forget it. So I say tangent of 2x is 2 tangent x over 1 minus tangent squared x. And I don't even need the quadrant for this one. So it's twice minus 8 over 1 minus 8 squared. Minus 16 over 1 minus 64. Minus 16 over minus 63 becomes 16 over 63. There's that one. So in some of these, you don't even need the quadrant. All right, that's probably a good stopping point. There's also half angle identities here. If you know an identity for the double angle in terms of the single angle, then you can just substitute back theta equals 2x and get a half angle formula. You can find the half angle in terms of a whole angle. So we'll do that next time. Try these ones out of, said before, do all of 7.1 from the supplement. 7.2, sorry, we already did 7.1. 7.2 from the supplement. Those are the sum and difference formulas. And then we can look at 7.2, we're just looking at. Guess numbers 1 and 2. This is the 7.3, number 2. For the double angle formulas. Okay. Well, that's quite enough for today, and there's a lot of formulas. Everybody online?